Hello and welcome to this Scion Instruments webinar on GC Method Development. Just a quick one today, I've just got 20 minutes, so it's just going to be a simple guide with hints and tips of what you should be looking for when developing your method. My name's James Hogan and I'm the Applications Lead Scientist here at Scion. So before we begin, I'm just going to give a quick introduction to the company. Scion Instruments is built on the history of Chromatography and Variant and is part of the TechComp group, having been acquired back in 2014. Scion Instruments design and manufacture a range of gas chromatography, liquid chromatography and mass spectrometry instrumentation. Some examples can be seen here. Our core GC platforms, the Scion 83 and 8500 GCs, are uniquely designed to enable extensive flexibility. Alongside these core products, we also offer standard method GC systems, which are pre-configured and complete systems that are fully validated for set methods. Alongside that, we also offer custom GC solutions, which is a fully bespoke configuration designed for any analytical need. These easy to use yet robust analyzers offer full flexibility. Method development is also available via our custom solutions and the applications team. The company prides itself in manufacturing in Europe at facilities in Hoos, the Netherlands, and its headquarters is based in Livingston in Scotland. Scion Instruments maintains a global infrastructure to support sales around the world. As well as providing support for Scion Instruments customers, there's also a service and support available for users of legacy variant systems still found in the field. So back to the topic of the webinar, which is method development, and the first question is, where do I start? So the first question we should ask is, what am I analysing? What are my target analytes and in what sample matrix are they found? Now, if we have the luxury, then we could make the choice on the hardware. So we could choose the ideal injector in the detector, but of course we may be limited by the configurations available to us. The next thing we should consider is the column choice. So really important is the stationary phase. So this needs to be suitable for the compounds that we're looking at. So for example, if it's a non-polar target analyte, then we should be looking at a 1 or a 5 phase column. If it's more polar, then perhaps a 624 or a wax column. Once we've settled on the phase, we can look at the dimensions. So the length of the column, the diameter of the column, and the film thickness can all play a big part in the analysis. When we've chosen our column, then the initial instrument conditions. So what are we going to set the temperatures and the flows at? So temperatures is particularly important as it needs to be high enough to ensure that everything that's introduced to the injector is volatilized and remains a gas. The oven temperature we want to ensure doesn't exceed our upper column temperature limit. And then the detector temperature also needs to be high enough to prevent any cold spots, anything crashing out and dirtying the detector. We may want to consider the injection type. So if we have a splitless, are we wanting to do a split injection, splitless, maybe even pulse splitless? And how much are we going to inject? Also, the runtime is important. There's a real balancing act to be had between having a fast enough runtime to ensure your throughput, but also being able to separate all the required analytes. Something that's also really important is the liner choice. So are we looking at a basic straight through? Are we looking at tapered? Do we want it to have deactivated wool in it? Are we looking at base deactivated liners or chemical coated? For particular compounds, this can really help reduce active sites and prevent tailing. And then there are other considerations. So for example, if you're doing liquid injection, so what is the solvent choice? What are you going to be diluting your samples with? You need to make sure that the target analytes are going to be stable in this solvent. And also the storage conditions are really important. So can you store them ambient? Would you need to store them in the fridge or the freezer? And how stable are these samples going to be? Are you going to need to prepare fresh samples every day, or will they last for weeks or even months? Here are a couple of QR codes, one for a GC columns guide to help you make the correct choice, and another for the liner guide to help you with your choice there. So once we've got our basic method conditions, the next thing that we want to do is optimize our method. So we've got our system set up, we've chosen our column, we've got that installed, and we've set some initial conditions that we think might work. So where do we go from there? So there's a few things that we're looking for. So one that's obviously really important is the resolution. You want to make sure that all the target analytes you're looking at are cleanly separated. I would always start with a high level or a concentrated standard. Ideally, you would run these individually, so then you can confirm your elution order, unless you're using a detector like mass spec, where you can use the spectra using a library search to confirm the identity. Once I've done that, I would create a mixed standard, and then I would run that, and that would give you confirmation that all the peaks are resolved from each other, there's no co-eluting, etc. The sensitivity is really important. So ideally we would run a low-level mixed standard, so you would dilute your standard at the desired LOQ, your limit of quantitation. So this could just be a simple liquid dilution of your mixed standard. Perhaps it's a gas, so you might want to use a gas divider or buy different concentrations of gas cylinders. If this isn't an option, we can go down the route of theoretical LOD, LOQ calcs, but I would try and avoid that and inject an actual sample, as it's much more likely to give you an accurate result. Other things we can consider in optimizing the method, so the injection volume we can play around with. I would be careful not to go too high, as this can have a really negative effect on your analysis. And the injector conditions as well. So are we looking at active ingredients, high level, high concentrated samples? So maybe we want to do a split injection where we vent most of the analyte, most of the sample, that's injected, because the target analytes are so concentrated, we'll still see them fine and we'll preserve the system. Or are we looking at real trace level analysis? So maybe we want to do a splitless injection or even a pulse splitless injection. The oven ramp as well. So this needs, as I said before, there's a balancing act here. So we're wanting it to be fast enough so that we have the throughput of our samples, but we're also wanting to make sure that we resolve all the peaks of interest. So here's another QR code. It's for a GC troubleshooting poster. So it's good to rule out any issues on the system that may be there that are affecting the method, rather than poor method development. So just to carry on from the previous slides, it's just a bit of a visual element to what I was talking about. So the first picture here is from our auto sampler. So it's some of the settings you can change that can have a big impact on how the sample's delivered, and therefore on your chromatography. So we've got different delays that we can set, pre and post injection delay. The injection speed, I find, is one that can really have an impact, and also the viscosity delay. If you're working with really viscous samples, it helps to ensure it's being drawn up and delivered properly. So this is showing the column flow. So the column flow should be set according to your column diameter. We can play with it a little bit. Here it's shown as a constant flow, so we can have it in constant flow mode, where the pressure will vary, or we can have it set in constant pressure mode, where the flow will vary throughout the run. Here you can see we have the pressure pulse enabled, so this is where we're doing a pulse splitless. So we're using this surge at the beginning to really push as much as possible onto the column. So it's great for trace analysis. One of the downsides, obviously, is that everything's getting pushed onto it. So your sample matrix is coming with it, so it may interfere with your target analytes. So just to give a visualization of the oven ramp, so here we have a really simple ramp. So we're starting at 50 degrees, we're holding it for a couple of minutes, then we're ramping at 30 to 200, and then holding it 1.5 minutes for a burn off at the end. So here's just an example of us adding multiple different ramps and different holds throughout, so you can find that this helps to separate. Where you're struggling to separate compounds, this can be really useful. So again, we're starting at 50, we're holding for 2 minutes, but then we're going to slowly ramp up to 100. So perhaps that's where we've got several components that we're struggling to separate, and then you can even have a hold in there as well to try and help that separation. And then at the end, if there's no longer anything that we're interested in, then we can very quickly ramp it up to our burn off temperature at the end there. So just a couple more visual aids for you. So the first two pictures here we have, this is the same compound that's been run on two different phase columns. So you can see the one on the left there is fronting really badly. The peak shape is awful, whereas in the second, the peak shape is much better. You're seeing that perfect Gaussian peak, and so it shows how important the column choice is to ensure that you get the right stationary phase that's relevant for your target analytes. We're talking about the oven ramp and separating components. So here we have some peaks that are co-eluting. So perhaps we can slow the oven ramp down and really separate them out. Perhaps we can use a longer column or change the film thickness to achieve this as well, or even the column flows. There's lots of things we can do to try and separate these out to give us the required separation. Here's an example of where we've gone really quite far. So yes, we've got fantastic separation now, but perhaps we've slowed the oven ramp down massively. So that's going to obviously increase our runtime hugely and may not be beneficial. Maybe we want the throughput, so the second picture there would do us fine and would be much quicker. So once we're happy with our methods, we've run the standards, we're getting great separation, we're getting perfect sensitivity, we've got a really quick runtime, perfect. The next thing we should consider is the sample matrix. So what are these target analytes found in? Depending on how you introduce the sample, which if there was a preparation technique, then the sample matrix itself could be present in a really huge concentration in comparison to the target analyte. So it's really important to take this into consideration. It may mean you need to consider adjusting the temperatures or the oven, the burn off, for example. The injector and the detector temperatures to make sure that the majority of what's in your sample isn't gonna condense out and cause you issues. So how are we going to prepare our samples and try and limit the matrix effect? So we need to consider an ideal technique for both your target analytes and also the sample matrix that these are found in. This may simply be a neat injection. Perhaps you just need to perform a simple dilution with a particular solvent, or it could be a more complex technique, for example, liquid-liquid extraction or solid phase extraction. Something else that we might need to consider is derivatization. So some compounds aren't particularly well suited for GC. So for example, there's some cannabinoids, also amino acids, that will degrade due to the temperature on the injector. There are ways around this, so we can, for example, use a Coulomb column injection where we slowly ramp the temperature of the injector, which will help prevent degradation. If this isn't available to us, then we could go down the route of derivatization. So we're reacting the target analytes to change the functional group to something that's then more suitable for GC. It's important to note that with these sample preparation techniques, you ideally should be subjecting the analytical standards to them as well, so then you can track if there's any degradation and make sure you get an accurate representation of what's found in your sample. Something else you can consider using is an internal standard. So these are this is where you add a different compound to all your samples, and this is usually of a constant concentration throughout all of your samples. And then instead of reporting or using the peak areas of your target analytes to calculate your results, you will use what's known as the peak area ratio. So you're dividing the peak areas of your target analytes by the peak area of this internal standard. This can be really useful and can help improve your variability of results and can really help reduce any effects, variations of the injection and also of any sample prep errors. So here are some more QR codes. So we've got an internal standard guide that explains in depth what they are, how to choose them, how to use them. We've also got guides on sample preparation techniques, and these can all be found in the Knowledge Center on the Scion website, along with others. So the final thing we should be doing when we're developing a method is to validate it in some way. So really put it to the test. So yeah, we've run a standard, we're getting good sensitivity, good resolution of all the peaks that we're interested in. We've introduced the sample matrix and made sure that's not had any effect. But really we should be validating the method in some way. So there are certain criteria that we should look to fulfill. So when we're validating a method, we're looking to test the ruggedness and the robustness of the method. So to really stress the method and see how well it performs over a number of criteria. So these validation criteria may well already be defined. So it might be an application or an industry specific one. For example, there's the Sanco guidance document that is used for import and export of chemical products and pesticides, and this details at great length all the validation requirements. Even if it's not defined, it really is best practice to check a few different requirements. So the specificity, so are we getting the resolution between the peaks? to make sure that there's no interference from the sample matrix and anything that we're not interested in. We want to make sure that our target analytes show good linearity, so that they're linear across the range of where we're calculating our sample. So ideally, really, we're looking a minimum of 20% above and below the expected concentration of the analyte, and you would want to run this over multiple points throughout that range. We'll be looking at the precision, so how repeatable is our method. So we would run multiple injections, repeat injections of the same sample, and we would check the RSDs for each target analyte. We'd also be checking the accuracy, so how close is it to the true value. One way of doing this really well is to run a recovery sample. So we would be spiking the target analytes into our sample matrix, and then we would run that sample through any sample prep. We would just prepare it as if it was a normal sample. Because we know what we've put into the sample, we then therefore know what we should get back out, and there we can calculate a recovery of that. Different guidance documents will provide different pass-fail criteria of this, and so something like Sanko is a useful document to use, even if you're not using it for this particular industry, but it's a useful guidance of whether your method is working well. So just something to briefly mention is our collection of Scion consumable kits. So the Scion consumable kits are really perfect for method development. So these are application-specific consumable kits, so they provide absolutely everything you need to get started. So from an instrument point of view, so your column, the liners, ferrules, septa, syringes, your sample vials. And these are industry-specific. So at the moment we have consumable kits for environmental applications, for VOCs, hydrocarbons, FAMEs, and pesticides, and there'll be more coming soon as well. So for each application, there are multiple kits available, and these are tailored to best suit your needs. If in any doubt about which one would suit you best, then please do get in contact with the Scion Applications team for assistance. This is the Scion Applications email. Please do get in contact with any questions about this webinar or any other method development and application needs. That brings us to the end of the webinar, so just a brief overview of method development. Thank you very much for your time today. Please do get in contact if you have any questions, and please visit the Knowledge Centre that can be found on the Scion Instruments website, where you can find all of our guides on method development, method validation, the sample prep techniques, different how-to guides and best practice, calibration guides, calibrating laboratory equipment. There's a whole host of information that will hopefully be useful for you.